My name is Ronald Germain, and I'm currently the chief of the Lymphocyte Biology section in the Laboratory of Systems Biology, which I also direct at the National Institute of Allergy and Infectious Disease at NIH in Bethesda, Maryland. And I started in immunology when I was 15. And many people ask how I decided at 15 to become an immunologist. And I was reading the Time Life book of science, and I saw a picture of a white mouse with a brown patch of fur. That was in utero tolerance from Billingham, Brent, and Medawar. And I said, that's what I'm going to do, and I've done it ever since. Convinced my mother to have a suburban household with several hundred inbred mice on the ping pong table downstairs. She became my first technician, held newborn animals while I injected them to give them graft versus host disease, while I transplanted thymuses, trying to cure them of that malady. Chased people like Jacques Miller around the world for advice under those conditions, and had the experience of 30 years later having him write me as the expert in antigen processing and presentation to say, how does this work? And my writing back saying, Jacques, you don't remember that 30 years ago I wrote you as a high school student asking for advice about thymic grafting, and it's really quite cool that now you ask me as the expert for advice yourself. The question of why any person really likes immunology, but particularly for a certain sort of generation of people who went into immunology, is, if you forgive the semi-religious reference, that it's in a certain level almost a Talmudic science. There was a period in which we knew it was enormously complex, knew very little about it, and you could argue about all the angels on the head of a pin and every different flavor of cell or anything else that went on in it. And that fit with my way of sort of rationally trying to discuss things and figure them out. But on a more scientific basis, immunology in particular has, like the brain in a different way, an enormous number of players that need to interact appropriately to give you a coordinated response. And my interest in science has always been driven by not trying to drill further and further and further down into little tiny details of a system, every water molecule in a crystal structure, but trying to put pieces together, moving up the scale of organization to see how something operates as a whole system. And immunology offers you a tremendous opportunity to do that in a very exciting way. Some people have said that immunology is really the original systems biology. You have to put all these different pieces together. And you now notice my lab title is a Laboratory of Systems Biology, and part of that is more or less the real hardcore computation, model building, omic scale work, but the immunology part is still built around putting the pieces together to see how the immune system really does its job, rather than just discovering a particular molecule and beating on its head for a long time. Immunology has changed enormously over time. There was a period in my youth and my training period when what used to be the early days of immunology and cytokine biology was called in the Yiddish the lymphodrek, the stuff that was in the funny supernatants, completely undefined. And real scientists in other fields didn't think too much of immunologists or immunology at that particular point in time. But immunologists wound up being the people who cloned a majority of these molecules. Much of biotech, aside from insulin, is driven by molecules that are involved in the immune system, either using antibodies as tools in various diseases or targeting diseases that involve the immune system. And so it's become much better defined, much more molecular, much, if you will, harder core, in a way that some people who grew up in the era where maybe it was a little bit more touchy-feely don't quite give immunology the respect it deserves, and I think they're making a big mistake in that regard. It's really quite a rigorous science when practiced extremely well. I think that the field found the work that we did and several other labs did simultaneously about a decade ago to bring dynamic in vivo imaging to the field as really a game changer in certain ways. That for all that people wrote about what the cells did in vivo, and they had sections and pictures of the cells sitting in one place or another, to actually see the cells moving, interacting, seeing how long they spend together, seeing what they do and where they do their business has really been one of the more dramatic changes over the last little while in the field. And I've been fortunate enough to be one of the people who's been able to help pioneer that activity and to continue to lead using those tools in understanding the immune system. So one of the questions that would come up, especially in times of tight funding, is why should immunology be especially funded? Why is this a good area for people to go into as a career choice? And that's actually a very easy question to answer, that as we've begun to explore various diseases, whether they're neurodegenerative diseases in the brain, whether they're metabolic diseases like type 2 diabetes, whether they're autoimmune diseases, other diseases of aging, which are really afflicting the population as we change our demographics, every one of them has a substantial signature of inflammation. And that's an important part of immunology. And so understanding how the immune system is contributing to those diseases is going to be absolutely critical in the health of the population going forward. And so it's virtually impossible to see how one can divorce progress in all those disease areas from immunology. And in addition, a lot of people are putting a lot of emphasis on stem cell work as a way of doing regenerative medicine in the future. It turns out that you can't graft stem cells from one individual to another any more than you can graft the kidney from one person to another without worrying about the immune system and whether it's going to reject the cells. And making the cells from the individual themselves and correcting genetic defects, which is another strategy that's going to be used, has its own problems. We know that if you give hemophiliacs the missing blood clotting factors, they make immune responses to those and often neutralize them, making it very hard to continue treatment. The same thing will be true if you put a gene back into an iPS cell. It will now become something that still can be seen as foreign by the immune system. So we're going to have to understand immunology for that purpose as well. So I think there's not a lot in contemporary medicine for the big problems in the world, whether it's emerging or re-emerging infectious diseases, whether it's these so-called degenerative or metabolic diseases or diseases of aging, or whether it's therapeutic applications, whether using monoclonal antibodies or iPS cells, where immunologists won't have to play a critical role.